We're past the point of asking if life exists out there. That was the old question. The one we asked when telescopes were still blurry, when planets were just dots of light, and when everything beyond our solar system felt like science fiction. Back then, you could still say, maybe we're alone, and it wouldn't sound naive, but not anymore. Because right now, we're not just guessing. We're collecting data. We're measuring atmospheres. We're detecting chemicals that on Earth come from things that breathe, eat, and die, things that live. With every spectrum analyzed, every biosignature detected, we're piecing together a universe that doesn't just hint at life, it practically shouts it. Take K218b, a planet that, until recently, was just another name in a long list of distant possibilities. Now, we found something in its skies, something that, on our planet, only comes from life, and if the numbers hold, it's not just a hint, it's the closest thing we've ever had to evidence. In 2025, the conversation has changed. We're not peering into the darkness, wondering what might be out there. We're analyzing signals, confirming readings, planning the next observations. The search isn't about hope anymore. It's about verification. We've moved past speculating about life in the cosmos. Now we're hunting for it with hard data. And it's not just one discovery. It's the pattern. Galaxies that form before they were supposed to. Planets that shouldn't exist but do. Signs of structure, complexity, maybe even biology in places we once thought were impossible. The silence of the universe is starting to break. Not with sound, but with light and chemistry and strange consistencies that keep pointing to one conclusion. Whatever life is, it might not be rare. There's a limit to how early something should be able to exist in the universe. Not because we said so, but because of how the laws of physics play out over time. Right after the Big Bang, everything was chaos. Temperatures were too high. Matter hadn't even clumped into atoms yet. It took hundreds of millions of years just for the first stars to form. Tiny, short-lived, chaotic ones made of hydrogen and helium. They didn't last long, and they weren't part of galaxies as we know them. Galaxies were supposed to come later, much later. That's what the model said. That's what made sense. But then Webb found Z14 in May 2025. It isn't just far away, it's far back. The light reaching us today left that galaxy when the universe was only about 280 million years old. In cosmic time, that's practically still the morning after the Big Bang. And yet somehow the galaxy already existed, not as a hazy, formless blob, but as a compact, organized galaxy full of stars. This compact dwarf galaxy, about 500 light-years across, with a mass of roughly 100 million suns, challenges our understanding of early universe dynamics. Here's the problem. Based on what we thought we knew, there simply wasn't enough time for this to happen. Galaxies aren't instant. They take time to build up, time for gas to cool, time for stars to form and cluster, time for gravity to sculpt the structure. The appearance of a mature-look galaxy this early throws a wrench into all of that. And this isn't the only one. Webb has been stacking up these kinds of discoveries for over a year now. Galaxies that are too old, too bright, too big for the era they're in. But MOMZ-14 is the current record holder, the farthest, the earliest. It pushes the timeline back even further and forces us to reconsider how fast the early universe was evolving. This is where things get uncomfortable because either our models of galaxy formation are missing something major, or there's something about the early universe we fundamentally misunderstood. Some scientists are now proposing that the earlier stars formed faster than expected. Others think dark matter may have played a more active role in organizing matter at the beginning. And then there are the more radical ideas, the ones that suggest the physics of the early universe might not have been the same as it is now. That maybe, just maybe, time itself moved differently back then, or that gravity worked in slightly altered ways before settling into what we now experience. We don't have the answers yet, but MZ14 is a clue, a big one. And it's not just a pretty image of a distant galaxy, it's a direct challenge to how we've been explaining the early chapters of the universe. What's most striking isn't just that it exists, but that it exists so calmly. It's not a chaotic mess. It looks structured. That's like finding a fully built city in the middle of a construction site before the foundation was even supposed to be laid. It shouldn't be there, but there it is with stars, with light, with structure, and that's what Webb is doing now. It's not just showing us the universe, it's showing us where our assumptions are falling apart. Every time we point it deeper into space, we're also pointing it further back in time. And the further back we look, the more we realize the universe didn't wait for us to understand it before it got to work. It was already building, already evolving, already creating complex structures faster than we thought possible. Z14 isn't just a galaxy, it's a message from the past, one we're still trying to translate. While Mumsy 14 raises questions about how early the universe got to work, there's something else much closer to home that's forcing us to ask a very different question. Not about when things started, but whether something out there is already alive, not imagined, not theoretical, not one day in the future, right now. That planet is K218b. It's about 124 light years from here, and for a long time, it didn't stand out. Just another exoplanet orbiting a small, quiet red dwarf. It was interesting because it sat in the habitable zone, the region where conditions might allow liquid water. But beyond that, there wasn't much excitement. Too big to be Earth-like, too strange to make the headlines. But then Webb looked at it, and in its atmosphere, it picked up something that changed everything. A signal that on Earth usually points to life. That signal was dimethyl sulfide, reported in a study published in January 2025. If you've ever stood near the ocean and caught that strong, salty sea air smell, you've smelled it before. That's dimethyl sulfide. On Earth, it's released almost entirely by tiny marine organisms when they die and break down. This gas rises from the ocean into the air. It doesn't last long. Sunlight and oxygen destroy it pretty quickly. So, for it to stay in the atmosphere, it has to be constantly replenished by life. So when Webb picked up traces of that gas in the skies of K218b, scientists didn't jump to conclusions, at least not publicly. There's always a long list of things that could go wrong. Misreadings, overlapping signals, or a weird chemical process we just don't understand yet. The gas could have been something else entirely, like methane, which shares some similar markers in the infrared spectrum. The cautious thing, the scientific thing, was to check. So they did. And the second time, the signal didn't just show up again. It came back stronger. Not only was dimethyl sulfide still there, but its concentration was estimated to be 1,000 times higher than what we find in Earth's own atmosphere. That's not a small signal. That's not a fluke. That's something pumping out gas on a massive scale. Now here's where things get uncomfortable. On Earth, there's no known way to get dimethyl sulfide into the air at those levels without something living doing it. We've never seen a purely geological or atmospheric process that can explain it. That doesn't mean it's impossible, but right now we don't have a better answer. And remember, this is a planet with a thick, hydrogen-rich atmosphere covered in a deep global ocean. If life does exist there, it's probably not like anything we know. It could be microbial, tiny organisms floating in the sea, reacting chemically to their surroundings. But if the signal is that strong, we might not be talking about just a few scattered microbes. We might be talking about an entire ecosystem, a living, breathing ocean planet. And if that's the case, then we've already made the most important discovery in the history of science. Of course, there are still steps before anyone can say that out loud. The data needs to be confirmed again, ideally by other instruments, by other teams. More observation and experiment could clarify whether K218b's DMS is a beacon of alien life or a chemical false alarm. For now, it's a thrilling clue. Even then, we'll need to rule out every other possible explanation: chemistry, geology, atmospheric physics. But if nothing else fits and the signal holds, then this isn't theory anymore. This is evidence, real, measurable, testable evidence. And that changes the entire conversation, because now we're not talking about whether life might exist in the universe. We're talking about how far along it is, what it looks like, what its chemistry is, how it survives, how it evolves. And that kind of question doesn't feel distant anymore. Not when the clues are already in the sky, drifting in from a planet just 124 light years away. We used to think of alien life as something we might find far in the future, something buried in fossils, frozen under Martian ice, or hidden on a moon orbiting Jupiter. But now it might be something alive right now, breathing into its sky, and we might already be watching it from here. There's something unsettling about recognizing yourself in the past, because once you see the familiar in a place it shouldn't be, you can't unsee it. It sticks with you. It raises a different kind of question, not about what's possible, but about when it should have been possible in the first place. That's what happened when scientists looked at an ancient galaxy named Julong. What made it different wasn't how far away it was, though it was far. What made it strange was how normal it looked. Julong isn't some warped, irregular blob like the other galaxies we've come to expect from the early universe. It isn't messy or chaotic or half-formed. It looks like ours. A spiral galaxy, structured, balanced, familiar. That's a problem because based on everything we thought we knew about how galaxies form, spiral galaxies like ours, big disk-shaped systems with swirling arms and central bulges, weren't supposed to appear that early. Not a billion years after the Big Bang. Not even close. Those first few billion years were supposed to belong to messy things. Young galaxies colliding, merging, blowing themselves apart, evolving slowly into the mature shapes we see today. Spiral galaxies were supposed to be the result of all that chaos, not something that showed up early and just stayed. But Julong challenges all of that. When Webb looked at it, it wasn't looking at something halfway there. It was looking at something that had already arrived. Its arms are visible. Its structure is stable. It looks like it's been in balance for a long time, which means it had to form even earlier than what we're seeing now. In other words, it had already gone through the violent part of its growth and settled into a mature structure. A structure like the Milky Way's within the first billion years of the universe. That's not just surprising, it's disruptive. It tells us that maybe galaxy evolution isn't a long, slow march from disorder to order. Maybe under the right conditions, some galaxies find equilibrium early. Maybe our models are too rigid, or maybe we're missing something fundamental about the way matter clustered in the early cosmos. Julong isn't just an outlier, it's part of a growing pattern. Webb is finding more and more of these early, well-structured galaxies in places where there wasn't supposed to be enough time or material for that kind of structure to form. The deeper we look, the more the timeline bends. And this isn't just about structure, it's about habitability too. Because galaxies like the Milky Way provide stability. They offer environments where solar systems can exist for billions of years without constant disruption, where planets can form, settle, and maybe even nurture life. So if galaxies like Julong were around this early, it means stable conditions, the kind that might allow life to emerge, could have existed much earlier than we thought. And that raises the next question. If life had the time, did it use it? We don't know yet, but what we do know is this. Our place in the universe feels a little less unique now. Our structure, our spiral, our quiet corner in a balanced galaxy. It might not be special. It might just be early or late. Either way, Julong reminds us of something we keep discovering with every new Webb image. The past doesn't look like what we expected. Sometimes it looks a lot like home. After looking so far out that we're literally staring into the beginning of time, it's easy to forget how much we still don't understand about the places right next door. That's why it caught people off guard when turned its attention to Neptune. You wouldn't expect a deep space observatory built to peer into the earliest galaxies to be looking at planets in our own solar system, but that's exactly what it did. And what it found wasn't just more detail. It was a reminder that even the familiar is still full of unknowns. Because Neptune, as it turns out, has been keeping secrets too. It's the most distant major planet in our system. Dark, icy, and rarely in the spotlight. Most of what we know about it comes from just one close encounter, Voyager 2, back in 1989. Since then, it's mostly been studied from a distance through blurry ground-based observations and passing glances from space telescopes. So when JWST finally turned its mirror in that direction, it was the clearest look we've ever had. And right away, something stood out. The auroras. These aren't like Earth's northern lights. Neptune's auroras are different. Less studied, less predictable, and far more difficult to observe. But Webb, with its infrared vision and ultra-sensitive instruments, picked up a complex, swirling light show at the planet's poles. It wasn't just a visual. This was data, detailed temperature maps, shifts in atmospheric chemistry, signs of powerful magnetic interactions happening far out in the cold edge of the solar system. So, what was causing them? Just like on Earth, Neptune's auroras are triggered by charged particles from the solar wind smashing into the planet's magnetic field. But Neptune's field is tilted, lopsided, and far more chaotic. And because Neptune is so far from the Sun, those particles take longer to arrive and behave differently when they do. Webb's observations reveal temperature variations across Neptune's atmosphere that weren't fully explained by sunlight alone. In some areas, the planet was cooling down unexpectedly fast. In others, strange heat signatures suggested internal activity or even unknown chemical reactions high in the atmosphere. These aren't just curiosities. They're clues. Clues about how magnetic fields work, about how energy moves through planetary atmospheres, and about how space weather behaves at the outer edges of a star system. And more than that, it's a sign that JWST isn't just for the deep universe. It's also a tool for looking inward with clarity we've never had before. Because sometimes the frontier isn't light years away. Sometimes it's just past Saturn. Neptune's auroras remind us that even after decades of studying our own solar system, there are still major pieces missing. The outer planets are still mysterious. Their moons are barely mapped. Their weather systems are largely unknown. And their magnetic fields, especially Neptune's and Uranus's, operate in ways we still don't fully understand. Webb gave us a better view, yes, but more importantly, it gave us new questions. And that's the pattern again. Whether it's a galaxy, a planet, or an atmosphere, this telescope doesn't just give us answers. It pokes holes in what we thought we knew and leaves us with better questions than we had before. It's easy to get lost in the individual discoveries. One planet shows signs of a strange gas. One galaxy appears earlier than it should. One world looks like our own in a time before we ever imagined that was possible. Each of them feels big on its own. But the real shift, the part that's harder to see unless you're really paying attention, isn't in the details. It's in the pattern. One by one, the universe is answering questions we barely knew how to ask. Not with anything loud or dramatic, just with data. Quiet, clear signals that tell us the silence we thought was out there was never really silence to begin with. We just weren't listening the right way. That's what's changed. The difference now isn't that we're suddenly surrounded by answers. It's that we've finally built a tool precise enough, sensitive enough, and stable enough to listen, to really listen. Not for vague signals, not for science fiction dreams, but for real physical signs that the universe has always been full of motion, full of structure, and maybe full of life. MZ14 forces us to redraw the early timeline of galaxy formation. K218b suggests we may already be watching something breathe in a distant ocean. Julong tells us our galactic structure isn't unique, and Neptune, our own planet neighbor, still has surprises we hadn't even looked for until now. But the bigger truth isn't about any one of those. It's about what they all mean together. Because now we know the universe didn't wait for us to understand it. It wasn't silent and it wasn't empty. It's been full of complexity since the beginning. It's been forming galaxies faster than we expected, building systems more stable than we assumed, and possibly allowing life to emerge long before we thought the conditions were even right. We've always wondered if we're alone. It's one of the oldest questions we've asked ourselves. But maybe we were never really alone. Maybe we were just blind. And now finally we're starting to see. Not everything, not clearly, but enough to know that something's out there. And for the first time in history, we're not just imagining it, we're measuring it. If you think what we're finding out there is surprising, wait until you see what's been hiding beneath the ice on our own moon.